Hello everyone. Today I want to talk about the shape factor and the elastic and plastic section modulus. We call shape factor as K and elastic modulus ZE and plastic modulus ZP. So I'm trying to explain in very simple words, and after all I will show how to calculate K for solid rectangle section. Here we have stress strain curve. When we say elastic, it means that the relation between stress and strain is linear. It means that when the load is unloaded from the structure, from the section, the strain coming back to the original point. It means that by reducing or increasing the stress, we have the same behavior for strain. But in plastic area, that is above the linear stage, we have extended or increased strain, but stress is going to increase to some extent, and after that it is generally stays in stable point or no changing after a limit. So here it's just very, for simplicity, I have rectangle section B width and H depth. It is the beam is under P1, P2, P3, and we have bending moment M1, bending moment M2, and bending moment M3. We assume that P1 is the least and P3 is the max, and P2 is in the middle. P1 has just elastic behavior effect on the beams. Stress is linear range, strain is linear range, and the same for P2 is increasing until we reach some point to Fy, but still the strain is linear because as a principle in structural engineering, the section should always be flat or flat plate, so it should be just strain should be always linear. But for stress, the stress is reaching to Fy in the extreme point, could be just one point or just two ends same time, but the rest of the section layers are less than Fy. And remember, it's just after Fy, the stress is not increasing, just transferring to the next layers and the next layers in depth of the section, trying to reach the Fy limit. And for P3, that's causing plastic moment. All section, especially for the maximum point, is reaching the plastic range. It means that the whole section depth experiencing Fy stress, but strain is still increasing in linear manner. So for another just slide for this one, we have one section. First P1 is applying epsilon 1, second increasing P1 to P2 cause epsilon 2, that is bigger than epsilon 1, but still linear distribution around the section, on the section, and finally epsilon 3, that is causing plastic or just collapse of the structure, collapse of the section, or just changing the section to hinge or releasing bending moment. We have epsilon 3 still linear, but for the same behavior under the loads for stress is just elastic area going to Fy, just start point for yielding, and after that stress is not going to increase and just transferring to the next levels, and after increasing the loads to the plastic point, we have Fy in all section. One side is tension, the other side is compression. So shape factor in strength of materials is called as the ratio of M plastic on M elastic, or the section capacity in elastic to plastic range to section capacity in elastic range. We know that from strength of materials, sigma Zp and sigma Ze are definition for MP, and sigma is Fy, in plastic range, and same for ultimate elastic range is Fy. So we can cross Fy from top and bottom, and we have just Zp on Ze, or section modulus in plastic range to section modulus on elastic range is called shape factor. Here I have just this explanation in a range of moment curvature curve, or the same for sigma epsilon or stress strain curve. Up to point A here we have elastic range for stress and strain, both are linear. When we reach to point B, strain is still linear but increasing, but stress is reaching to Fy final point and transferring to next level, and it is the Fy is the extreme point for stress. And same for point C, still strain is increasing linear, and stress is reaching to Fy stress is reaching to next layers until covering whole section around neutral area, neutral point. And same for point D, whole section is still experiencing increased strain, but the stress is going to cover fully in Fy, and finally in epsilon in point E, the section is collapsed and the section can't take any bending moment. We say collapse point, and whole section is under Fy. This is section view, and if we want to see in the superstructure view or just beam view, for example, I've chosen two simple strain on the beams, restraint on the beam. So if we have just simply supported beam on the load, and the load is increasing until this maximum bending moment point reaches plastic, and it is coming hinge. So we will have one hinge, second hinge, and third hinge in one row, in one direction. So the structure is unstable, and we say it is collapse point, and that is the end of the structure, or structure reaches to it is maximum plastic strength. And same for fixed beam, two ends fixed, and you know that this area, the end areas have maximum bendings applied to load, and the third point in the middle of the beam is just experiencing the bending moment as well, but less than two edges. So the first point reaching to hinge point or collapse point are the two ends, and if we increase the load, still this beam is still stable because it is just two hinges at two ends. It is like simply supported beam, and if we still increase the load, it means that the structure has still capacity to yield or to collapse. And if we increase the load, the third point that has the maximum bending moment now reaches the collapse point or fail point, and we have three hinges, 1, 2, 3, three hinges in one row, and section is unstable. So the load causing all these three hinges to appear in the structure is called, or just they call the load that's causing plastic bending moment, and it is the maximum yield strength in plastic, and it gives normally better capacity of the structure. The plastic range means that the structure can take much more loads and absorb loads, and it can deflect more, or we just technically we say that it has much more ductility. And here from that equation we can see that the MP value is higher than ME value by multiple of K factor. K is the property of characteristics of section, and it is unique for each section. So I have one example for rectangle section how to calculate shape factor or K value. For K value, we need to have stress distribution because after all, we need to calculate M value for strain for elastic and plastic range. For top side, we have same section BH dimensions for the section, and this is stress distribution, ultimate stress distribution. We have Fy stress at two extreme points, top and bottom, and this is 3D view of the stress distribution on the section. So we have two rectangle section for stress distribution for tension and compression, and the distance between center to center of these loads to cause the bending moment against the applied load is C times 2/3 of h or T times 2/3 of h. So T or C are equal to Fy from this equation. We need just to have volume of this stress block to have T value. This is F by B H over 2 times half, that is area of this triangle, times B, third dimension, and same. So this T or C times 2/3 of h gives the bending. So F by B h onto over half times 2/3 of h gives B h squared on 6Fy. So you know that here for I, or just moment of inertia, is just BH3 on 12. That's for solid rectangle, and Z is always I on Y, or just depth until the neutral axis. And for rectangle section, we have BH squared on 6 for Z. We say Z in elastic range. For plastic range, we need to go for stress distribution block and calculating M value. So this is the stress block, fully yielded. We have Fy all section, half is, for this one, half is in tension, half is in compression, and the distance between these two are half of h, total depth. So this is 3D view, and third dimension is B. So we can calculate T and C values from this equation. M is C times half of h, or T times half of 2, or center to center of these two loads. And we know that here T is the stress block in 3D view, that is just area of this half rectangle, or this rectangle, the bottom rectangle, to third dimension, that is B here, gives T value. So for M, we need to multiply this T value to the distance between C and T, that is half squared, that is half of h here, and finally M is F by B h squared on 4. So ZP, that is M on Fy, is B h squared on 6. Here we see that modulus of section in elastic range is BH squared on 6, and for plastic range is BH squared on 4. So K, that is shape factor for this solid rectangle section, is ZP on ZE, or MP on NE, is equal to BH squared on 4 divided by BH squared on 6, and finally K is equal to 1.5. That is unique number for this shape. And remember, for all shapes we have unique number. For example, for solid circle, shape factor is equal to 1.7, which means that the yield or plastic bending moment, or the bending capacity at yield point for circle section, solid circle section, is about 1.7 times of the ultimate bending for elastic range. And remember, when you design, always we have safety factor as well that needs to be applied for if you want to just design or just calculate the capacity in elastic or plastic range. Thanks so much. Thanks for watching the video.